By the end of this session, you'll be able to calculate acceleration, define uniform and non-uniform acceleration, you'll be able to define velocity and displacement, and be able to interpret velocity time and displacement time graphs for uniform acceleration. Accelerations are all around us. If you've ever used a catapult, then you've had to accelerate the stone as it flies away. Every time we walk, we have to accelerate and decelerate ourselves. If you're driving a digger, then you have to accelerate and decelerate the bucket in order to dig. Now these accelerations change from moment to moment. They're non-uniform accelerations. And if we want to measure them, then we would have to measure over and over again. In physics, we often find it easier to start thinking about acceleration that is uniform. That is, acceleration that is the same from moment to moment, that's constant over the time period that we're interested in. Now, you've met acceleration at GCSE, and in GCSE, you'll have thought of acceleration as change in speed divided by time. But in Physics A-level, we need to think about change in velocity. You'll remember velocity is a vector quantity, so it has size and direction, and it's important what direction the velocity is in. So in A-level physics, we say that acceleration is change in velocity divided by the time taken for that change. So we can write that as the final velocity minus the initial velocity divided by time. Remembering that in A-level physics, we use u for the initial velocity and v for the final velocity, we get this equation for acceleration. Now those are the units. Of course, the units of velocity and speed are the same, meters per second. Acceleration is in meters per second squared. And remember, because velocity is a vector, acceleration is also a vector. That's very important to remember in questions. Direction is important. So, let's have a look at this simple question. A car can go from 0 to 26 meters per second in 10 seconds. And its acceleration, if we put that in, its acceleration is 2.6 meters per second squared. Now, as well as using numbers to think about acceleration, we can use graphs. And what we're going to look at now is we have a ball that's going to roll down a slope. We're looking at vectors, so we want to find out how is the displacement of this ball along the slope going to change with time, and how is its velocity and its acceleration going to change with time. Remember, they're all vector quantities. So let's have a look at that. Can you sketch what you think the displacement time, velocity time and acceleration time graphs would look for this simple